Hi everyone. Today we're going to look at prestressed concrete and figure out how beneficial is the prestressing process based on some estimates from common failure theories. When you look at a lot of infrastructure like bridges and buildings, they often include these large unsupported spans of concrete that might have heavy loads on them. These spans of concrete are essentially beams that are supported on both ends, and due to the forces of gravity and loads like trucks and trains, they can develop large bending moments, which gives a flexural stress distribution that's compressive at the top and tensile at the bottom. The problem is that the tensile strength of concrete is pretty low, which causes cracks to initiate at the bottom of the beam. However, the compressive strength of concrete is about 5 to 10 times higher than the tensile strength. So what engineers commonly do is to apply a compressive prestress to the concrete sections using steel cables that are under tension. This shifts the stress distribution so that there are larger compressive stresses, which concrete is good at accommodating. This allows the concrete beam to withstand a lot larger forces overall. There are some great videos that expand on some of the concepts behind prestressed concrete, and I'll include a few of the links below. But in this video, we'll formulate an example question based on undergrad level knowledge of failure theories to think about some of the numbers behind how beneficial this prestress process can be. I'm not going to explain all of the concepts behind failure theories because there's already a great video about that which is linked here. So I'll just give a quick summary. There are different failure mechanisms for materials that are brittle and ductile. Brittle materials include things like ceramics, glass, some types of polymers, and of course concrete. Brittle materials most commonly have much larger failure stress under uniaxial compression than under uniaxial tension, and we label these as sigma UC and sigma UT. In this case, we'll use Moore's failure criteria for failure. When the principal stresses are both positive, so we're in this top right quadrant, our failure condition is when the first principal stress becomes larger than the ultimate tensile strength. Similarly, when both our principal stresses are negative, our failure condition is when the second in-plane principal stress becomes larger than the ultimate compressive stress. When we have one positive and one negative principal stress, the failure boundary is given by the equation of the line between the ultimate tensile and ultimate compressive stresses. Ductile materials include most metals and polymers. Two of the most common failure theories for ductile materials include the max shear stress theory and the max distortional energy theory. The max shear stress theory tells us that failure will occur when our calculated absolute maximum shear stress is equal to 1/2 of the experimentally measured uniaxial yield stress. This gives us a failure boundary consisting of straight lines. The max distortional energy theory involves calculating the von Mises stress given by this equation and comparing that directly to our experimental yield stress. This gives an elliptical failure boundary. Again, if you're not familiar with failure theories, it might be a good idea to watch the previously linked video before moving on. We normally cover failure theories as the last topic in the course on mechanics. So the prerequisite knowledge includes Moore's circles and shear force and bending moment diagrams. We're going to look at a problem where we determine how valuable is the prestress and how much prestress should we apply. I know this looks super long, but we'll go through each part one at a time. We'll start in part A by calculating the distributed load that would cause failure in pure concrete. In part B, we'll develop a set of equations that allows us to calculate both the ideal prestress and the distributed load that would cause failure in this prestressed beam. In both part A and part B, we'll use a beam that's 0.4 meters in both the height and width. In parts C and D, we'll calculate the size of steel cables that we would need in order to apply this prestress on the concrete beams, using our two different failure theories for ductile materials, since most types of steel are ductile. As always, we'll start by making a free body diagram and writing our equilibrium equations. Here, we're approximating our distributed load as a point load in the middle, with a total magnitude that's given by the distributed load with units of newtons per meter times the length of 8 meters, which gives us 8 p naught. Based on symmetry, we can expect that each of our reactions will be equal to 4 p naught, but we can also write out our sum of forces and sum of moments to confirm this. Next, we can draw our shear force and bending moment diagrams to understand what's going on along the beam. For the shear force diagram, we're starting at the reaction of 4 p naught, and we have a constant negative distributed load that brings us down to negative 4 p naught at the end of the beam. The moments are 0 at both ends, and the slope of the moment is equal to the shear force. So we're starting at x equals 0 with a positive slope. The slope of the moment becomes 0 in the middle of the beam and then becomes negative. The maximum moment is going to be the integral of the shear over the first half of the beam, which gives us 4 p naught times 4 meters divided by 2, giving 8 p naught. Now we might look at this and ask how the moment can have the same units as p naught. Our distributed load, p naught, has units of newtons per meter, but we multiplied it by 8 meters here, and then multiplied it again by 4 meters here. So it does actually have the correct units here of newtons times meters. It's just that we've already subbed in our numerical values for the lengths. So where would we expect this beam to fail? For long, thin beams, the flexural stresses are usually much larger than the shear stresses, and we'll do a quick check of that. We can calculate the max shear stress, which occurs at the maximum shear force, which gives 37.5 p naught. We can calculate the max flexural stress, which occurs in the middle of the beam, as being 750 p naught. So the flexural stress is much larger, but they're also in different locations. Our shear stress is largest at the ends of the beams near the neutral plane. In the middle of the beam, the flexural stresses are dominant, and the shear stresses are negligible. So we can conclude that the failure will occur in the middle of the beam, and the shear stresses can be neglected, which is exactly why I chose this particular loading condition. Since we know that failure will occur due to flexural stresses in the middle of the beam, we'll look at 2 points on the cross-section, with A being at the top under compression and B being at the bottom under tension. Point A is in uniaxial compression. If we draw our Morse circle for uniaxial compression, we can see that the first principal stress is 0 and the second principal stress is given by the flexural stress. Similarly, point B gives us a first principal stress that's equal to the flexural stress and a second principal stress of 0. If we look at our failure boundary for brittle materials, we can think about what happens as the value of the distributed load is increased. Point A will move downwards along the sigma p2 axis, and point B will move in the positive direction along the sigma p1 axis. Point B is going to reach the failure boundary first, giving this as our failure condition. So our failure will occur when the magnitude of flexural stress is equal to 4 megapascals. We can sub in the numbers to find out that our distributed load is then 5.33 kilonewtons per meter. And this is the distributed load that will cause failure in our pure concrete beam. Now we can start looking at the prestressed concrete. In the absence of any distributed load, the uniform compressive force on the beam gives a compressive force at all points in the concrete, so that both points A and B have the same value of a negative principal stress 2. As we increase the distributed load, the flexural stress makes the stress on point A more negative, while at point B, the total normal stress will become more positive and eventually become 0. As we keep increasing the distributed load, point A continues to become more negative, and point B switches to moving along the principal stress 1 axis of our failure boundary diagram. the largest value of the applied distributed load that the beam can withstand will occur when point A and point B reach the failure boundary at the same time, which is given by the two equations we have here for the second principal stress at A and the first principal stress at B. We can copy these two equations onto our next slide and substitute in our moment as being 8p0. This gives us two equations with two unknowns, the unknowns being large P, our applied axial force, and p0, our distributed load. We can add these two equations to get an equation for large P. Once we simplify and sub in our numbers for the area, we find that this force is 1.28 meganewtons, which is a really large force. We can subtract the two equations to find an equation only in terms of our applied distributed load. When we sub in the numbers, we find that this gives us a distributed load of 16 kilonewtons per meter, which is exactly 3 times larger than what we found for the concrete beam without prestress. So this is a pretty large improvement. We're actually increasing the load capacity by 3 times. Part C of the question asks us to determine the radius of steel cables that we need to apply the prestress. And we're asked to use the MDE theory. The equation for the von Mises stress is a function of the two in-plane principal stresses. However, these steel cables are under uniaxial tension, so they have a positive principal stress 1 and 0 principal stress 2. This really simplifies the equation for the von Mises stress to equal the first principal stress. We're also asked to use a factor of safety of 2, and we can sub that in at this point, which tells us that our first principal stress should be 150 megapascals. Since this is simple uniaxial stress, we can use our general equation for engineering stress as being the force over the area. We're assuming at this point that the force on each of the fibers is the same, which is why we're dividing P by 4. This is actually not a very good assumption, but accounting for the different stresses in the top and bottom cables would make the problem a little bit too complicated for what we want to do right now. By rearranging to solve for the radius, we can find that we need a radius of 0.2026 meters, which is a diameter of 5.2 centimeters. We can also think about how much of the cross-section this represents. If we divide the area of steel by the total area of the cross-section, we get around 1 over 18.8. So by making only about 1/20th of the beam out of steel cables, we can get about 3 times higher load capacity, which is why prestressing concrete is so common. Part D asks us to calculate the required radius if we were using the max shear stress theory. The central concept of the max shear stress theory is that the failure occurs when the max shear stress equals to half the yield stress. We can certainly do the calculations to determine the steel cable diameters. However, let's first look back at the diagram of the failure boundaries for the MSS and MDE theories. We can see that there are 4 points where they exactly overlap, when the principal stresses are equal, and in cases of positive or negative uniaxial stresses. In this case, we have uniaxial tensile stress on the steel fibers, which means that the failure conditions for MSS and MDE are actually going to be the same. So we don't need to do any calculations. We already know that the answer will be the same as for the MDE theory. This is a really common question that I like to include in exams because it tests conceptual understanding about the failure theories. Students who can recognize that we're at one of these 4 conditions can get the answer in a few seconds, while students who don't recognize it can still calculate the correct answer using equations. From our uniaxial Morse circle, we can see that the max shear stress is equal to the radius of the circle, which is half of the principal stress 1. Now we have that our max shear stress is equal to the first principal stress over 2, and it's equal to the yield stress over 2. And at this point, we can sub in our factor of safety. From there, we find that our principal stress 1 is 150 megapascals, which is the same as what we found for the MDE theory, and of course gives us the same radius. We analyzed a prestressed beam that looks like this, with the prestress as a uniform value over the ends of the beam. The reason we did it this way is to make it simple enough to analyze with undergrad mechanics equations. However, real prestressed beams typically have a non-uniform distribution of stresses that make the prestress process even more beneficial. For example, the steel cables can be included only at the bottom of the beam, or that they can have a complex distribution that causes the beam to actually bend upwards when no external stresses are applied. This upward bend is exaggerated in the image, and in reality is probably not something you would notice visually, but does have a large impact on the mechanics of how much weight the beam can support. Well, we found that our simple prestress can improve the force capacity by 3 times. These advanced designs might achieve 4 or 5 times, but you'll probably have to use finite element calculations to analyze and design them. So in summary, we learned that concrete is stronger in compression than in tension. And that's why engineers often pre-stress concrete to allow it to withstand much larger transverse forces. When our stress is uniaxial, the MSS and MDE theory for ductile materials predict the same failure stresses. And we talked about quickly how real pre-stressed concrete has a more complex distribution of stresses. At this point, I also want to remind people that if there's anything you're wondering about the mechanics of everyday objects or things that you've observed, it's great to get suggestions from you about what types of things to cover in future videos. So you can either contact me through this channel or you can contact me on my Purdue email.